Yes, good afternoon.
Yes.
Okay, thank you. So yeah, let's start with today's lecture. But before, I guess that you already submitted homework 1, right? I hope it went well, and the deadline for homework 2 will be next Friday. Yeah. So let's start with today's lecture. Let me start recording this, and then I share my screen. Can you see my screen, my slides?
Yes, we can.
Yeah. Okay. Thank you. Because today I will be using the my iPad because we will do some exercises together, and let's see how that goes. So in today's lecture, we will be talking about the mapping of quantum circuits and also the mapping of fault-tolerant quantum circuits. But before going into that, I would like, as usual, to start with a summary of the last lecture. And on Friday, we talk about one of the most promising quantum error correction codes that is called surface code. Do you remember why this code is so promising? What are the main good characteristics of this code? No, nobody. So this is one of the most promising quantum error correction codes because it has a very simple structure in terms of topology. So as you can see in the slide, it's just a 2D array of qubits with nearest neighborhood interaction, which is feasible to implement in current quantum technologies. And the other good feature of this code is like it has a high error threshold. Do you remember what the error threshold is? How we can calculate it, what kind of graph we use to let's say to visualize the threshold, to calculate the threshold of a code?
It has something to do with the error rate of the logical qubits versus the error rate of the physical qubits, right?
Exactly. When we talk about the threshold, we show this graph in which in the x-axis you have the physical error rate and in the y-axis the logical error rate, right? That you can achieve with that code. And yeah, and this, so when you plot that graph, logical error rate versus physical error rate for different distances, when they cross, that defines the threshold of your code, right? And do you remember what happens below that threshold? Below that point? And above that point? Anyone? So the threshold defines how many errors your code can, or the physical error rate that your code can tolerate, right? So you remember, so below the threshold, when you increase the distance, you can get lower logical error rates, and above the threshold, it doesn't matter if you use a quantum error correction code or not. In this case, surface code, that you'll not will have lower logical error rates. In other words, it's better not to use a code if you are above the threshold of that code. Now we also talk about a specific form we discussed, let's say, 2 ways of encoding logical qubits in surface code. Do you remember what are those 2 types of logical qubits in surface code? You can look at the slides from last week. They are on white space. Anyone? Sorry. No? So we discussed also 2 ways of encoding logical qubits in surface code. The one is planar surface code, in which it's just a patch or a sublattice of your of your array of qubits, and the other one is the defect-based surface code, in which you can create holes within the lattice. And depending how you encode your logical qubit in surface code, the logical operations will be, you will need more or less physical qubits per logical qubit for the same distance, and also the logical operations will perform in a different way. Then, at the end of the lecture, we discuss a specific case, a specific distance tree kernel substrate code that is called the Ninja Start, and we will also look in how to perform logical operations in it and how to perform quantum operation cycles. So today we are going to change topic a bit, and as I already mentioned, we are going to talk about the mapping of quantum circuits on quantum devices. The mapping procedure, as we will see during this lecture, consists of 3 steps that are called initial placement of qubits, scheduling of operations, and routing of qubits. So during today's lectures, we will discuss and we will go into detail on these 3 steps. But first, let's start. So what does mapping mean? So imagine that you have a quantum algorithm, and as you may know, a quantum algorithm can be described by a quantum circuit when you assume or when you use the circuit model of computation. But this circuit has to be run on a specific chip with specific topology. Like for example, here to the array of qubits. So can anyone give me a definition of mapping? So what does mapping mean? Mapping of a quantum circuit or a quantum algorithm?
I guess it'd be at each like time step in your circuit with what's the mapping from like the logical qubit indices to the physical qubit indices.
Okay, so you mentioned 2 things. So the mapping of the logical qubits, that I guess that you mean the qubits in your circuit, right? In the picture above. How they are mapped into the physical ones to the array of qubits in this case, right?
Yeah.
And the other thing you mentioned is time step. So the order in which operations are performed, right? That's what you mean?
Mm-hmm. Yeah.
Yeah, exactly. So the mapping problem, if I have to give a definition for the mapping problem, it can be defined as giving an input quantum circuit. You will have to modify it to satisfy all quantum device constraints while trying to minimize the number of additional gates and circuit depth in the final hardware compiling circuit. What does it mean? That as I think I already mentioned, some quantum chips have several constraints. One of them, most common one, is the limited connectivity between them. And that means that given a circuit, this description of the algorithm in a circuit is hardware agnostic. So for example, it assumes that any qubit can interact with each other, but that might not be the case. That's why you have to modify and to adapt the circuit into a different version that respects all those constraints and therefore is executable or runnable on your quantum chip. As I just mentioned, the mapping process consists of 3 main steps. That is the placement of qubits, the scheduling of operations, and the routing of quantum states. And usually this is done in the compiler, in the quantum compiler. Remember in the second lecture, I think we discussed about compilers, and now one is the fundamental passes of the quantum compilers. And of course, those 3 steps that compose the mapping process depend on the quantum processor characteristic or the constraints of the processor. Now, just let's give an example. So imagine that you have the circuit on the left, that is just the gray code circuit, very simple, that consists of 6 qubits. And on your right, you can see the layout of the coupling graph, also called coupling graph for a specific chip. This is surface 7, in which each of the circles is a qubit, a physical qubit in your device, and the arrows, the possible interaction. In this case, this double arrow means that you can do a signal from Q0 to Q2 or from Q2 to Q0. So the first thing that we need to do, as your colleague just mentioned, is to place the logical qubits, or also called virtual qubits, so the qubits in your circuit, in your physical device. If you do that in a smart way, taking into account the interactions between the logical qubits, so for example, A and B need to interact, also B and C and D, and so on. So taking into account the 2 qubit gates, you can place the qubits in the logical qubits in the physical qubits of your chip in a way that all these interactions are satisfied. that, for example, if I place A in Q0, E Q1, B Q2, D Q3, and so on, all qubits can interact. For example, A and B are next to each other, B and C are next to each other, C and D are next to each other, and so on. But what happens if I'm not that smart and I just say, you know, I'm going just to place the qubits, my virtual qubits or my logical qubits in the physical ones just in order. That, for example, I put A in Q0, B Q1, C Q2, D Q3, and so just in the order they appear. As you can already see from this picture, in this case, A and B, they don't share a connection, therefore they cannot interact. The same happened with B and C that are placed in Q1 and Q2, so they cannot interact neither. So what to do in that case? In that case, what we need to do is to insert some swaps, or what is also called routing on qubits, in order to make those qubits nearest neighbor, or in other words, to place them in adjacent positions. Of course, when you add swaps to your circuit, you increase the circuit depth and the number of operations. And for example, before I forgot to mention, so in the previous case in which we had, like, say, an optimal placement of qubits, it required 5 time steps. In this case, we require 11 time steps because we had to add some swaps. But can we do a bit better? Yeah, of course, we can also take the same circuit and we schedule the operations. Scheduling the operations means to perform some operations in parallel when there are no dependencies between them, and we can decrease the circuit depth from 11 to 9. Why is it so important to decrease the circuit depth, the number of time steps in your circuit?
There's a limited coherence time in the hardware.
Exactly. So especially this is especially critical, especially key in the NISQ era, because we in principle we will not use any kind of quantum error correction. So you are limited by the coherence time of the qubits, right? So the lower the circuit depth, the better, or the higher fidelity of your algorithm. Yeah. Now let's just see one other example. As I just mentioned, the mapping, so it's just to transform the circuit to satisfy the target quantum processor constraints. So here you have an example of another circuit that is composed of 7 qubits and a description in the Quasum instructions, or Quasum code. And imagine that you want to run this circuit in this kind of chip that is, again, in this case, a 2D array with near-zero interaction. So as I just mentioned, the first thing, or one of the things that you can do is, and not in this order, is to schedule the operations to leverage the parallelism of them, right? Instead of doing one operation after the other, you can just perform some operations in parallel in order to save some cycles or steps in your circuit. Then again, the other thing that you need to do is to place the logical qubits into the physical ones. And again, you can do it in a kind of random way, just one-to-one mapping, so Q1 in your circuit, Q1 in your physical device, and so on. Or you can take into account the interaction between them, or the number, in this case, the number of C-nodes, and between each pair of qubits in order to place them already next to each other in the chip. In this example, as you can see, the first C-nodes in the first cycles can be executed. For example, in the first step, Q3, Q4, they are next to each other, so they can interact, no problem there. The same for the C-node Q3, Q5, Q3, Q5, they are next to each other, that's fine. However, there are these two C-nodes, 0, 5, and 2, 3, that they are not next to each other. So you look at the picture of the layout, the square in the middle, in step 3, 0 and 5 are not next to each other, and 2 and 3 are not next to each other. That's why, in order to allow them to interact and perform a C-node, we have, as I mentioned before, to add some extra swap operations there. And this is what is called, as I just mentioned, the routing of qubits. Actually, we call it routing of qubits, but what we do is to route the quantum states, not the qubit itself. I think it is clear from these two examples that when you need to map an algorithm to a specific device, you increase the number of operations because you add some swaps, as well as the circuit depth. And of course, this impacts the fidelity of your algorithm, because the more gates you add in your circuit, And the more, the higher the circuit depth, the lower the probability of success of fidelity of your algorithm, because of the coherence and because of because anytime that you perform an operation, you increase the probability of introducing an error in your system. Now, what are those constraints? So far, I've been focusing only, let's say, on the connectivity constraint. Here you can see the layout of the coupling graph of different IBM chips, in which again the circles represent the qubits, and the arrows the possible interactions between them. Something that I didn't mention, but is also considered as a constraint, is the primitive gate set. As we discussed before, all chips, quantum chips don't support any kind of gate or rotation, but just a limited set of gates that are universal. For example, in this case, the IBM chips only support single qubit gates, some unitaries, and a CNOT gate. And of course, any circuit before being run on such as devices, all the gates of those circuits need to be decomposed to the primitive gates. Now, let's have a look again at the coupling graph or the layouts presented here. So as I mentioned, the circles are the qubits and the arrows are possible interaction. But in this case, you see the arrow, it's only in one direction. What do you think that means? An arrow, for example, just going from Q0 to Q1.
Like you could only use, like if you did a CNOT, only one of them can be the target and the other one the control, like you couldn't do it the other way.
Exactly. So in this case, you don't only have the connectivity constraints, so what qubits can interact, but also the way that can interact. For example, in the IBM QX2, a CNOT can be performed from Q0 to Q1. That what I mean by that is Q0 is the control and Q1 is the target, but not the other way around. You cannot do a CNOT between Q1 and Q0, Q1 being the control and Q0 being the target. So how to solve that? So in order to solve that, you can use different, let's say, decompositions in which you can change. So here on the right in figure A, you have a CNOT between PA and PB. And in order to change, let's say, the direction of the CNOT, you can just add 2 Hadamars before and 2 Hadamars after. In that case, I can reverse, let's say, the control and the target, the control and the target. There are also other tricks, like for example, in B, in which I have to do, again, a CNOT between PA and PC, but I have a qubit in between. So imagine that I want to do a CNOT between, let me see, this one, Q12 in IBM QX3, figure C, between Q12 and Q4. In order to do that, I can just perform these 4 CNOTs that are shown on the right. Also, in order to do a swap between 2 qubits, I can also do 3 CNOTs, and in those 3 CNOTs, you see those 3 CNOTs, they are in let's say, from control to target, and the other goes target control. So again, in order to reverse the direction of the CNOT, we can just play the same trick as I mentioned before, in which you add Hadamars in between. Okay, so what I would like to emphasize here, that here is not only the connectivity constraint, so what qubits are allowed to interact, but also in what way they are allowed to interact. Now let's talk about surface code 17 of the Ninja star. So on the left, you can see the picture of the Ninja star that we were discussing last week. And on the right, you can see the layout of the chip that has been implemented here in Delft of such Ninja star. So on the right picture, each of the circles represent a qubit, of course, and the orange coupling buses between them. So the orange things are the possible interactions or interconnections. Here you can see that each of the qubits has a different color. Do you know why is that? Something about frequencies?
Does it just mean that each has to have a different like resonant frequency?
Exactly.
They
So-
can't, the gates don't like interfere with each other.
Yeah. So in superconducting qubits, you can tune the qubits to a specific frequency for operating them. In principle, I mean, you only have, for example, 5 qubits. You can tune each qubit to a different frequency, and that is the one that you will use, let's say, again, for controlling and operating those qubits. However, imagine that you have a lattice of qubits with thousands of qubits. You cannot have thousands of frequency. So something that was proposed and scheme that is being used is to reduce frequency. That means that qubits on the same color, they use the same frequency for operations. But I will come back to that later. So as I said here on the right, this is the chip layout of surface code 17. However, the goal of the team here in GDoc is not only to build, let's say, one surface code 17, but to build something that is scalable and we can go to higher distances, right? Because as I say, surface code 17 on the Ninja Star is just an example of distance 3 surface code. But what if you want to go to distance 5, to distance 7, and so on? How you can build up, let's say, a hardware or a device that is scalable. So in 2016, they proposed the following design, in which in the figure of the left, you can see this like kind of cell with 8 qubits, that this is a unit cell that just by copying and pasting it or replicating it, you can build larger surface code, like for example, the Ninja Star on the right, okay? So, but this surface code 17, this is a Ninja Star. So the goal of this chip is to show that indeed one logical qubit has lower error rate than, let's say, 17 physical qubits. But this chip can also be used as a 17 physical qubits to run an algorithm, right? So if you would like to run an algorithm on this kind of device, any kind of circuit, what are the constraints of this chip? The first one, as I said, is the primitive gate set. So any quantum circuit or algorithm has to be decomposed into the gates that are supported by the chip. In this case, surface 17 or Ninja Star supports X and Y axis rotation, and the primitive 2-qubit gate is the control phase or CZ gate. That means that if you, for example, want to implement a C node, you have to do it with 2 Hadamard and a C phase that is similar to a C node, corresponds to a C node. So again, what are the constraints of this chip that you have to consider whenever you want to run a circuit on it? The first constraint is, as before, is due to the limited connectivity between the qubits. What does it mean? So we see at the layout, the arrows here, those means that the possible interactions or interconnections between them. That means that, for example, qubit 0 can perform a CZK or can interact with qubit 2 and qubit 3, but not with qubit 6, and so on. So it's the same things that we discussed before. There is another constraint that is in terms of measurement, because as you can see here in diagonal, you have different feed lines. So different qubits are coupled to different feed lines. For example, qubit 13 and 16 are measured through feed line 0, and for instance, 14, 10, 7, 4, 1, 5, 8, 11, 15 are coupled to feed line 1. And that imposes some restrictions when you want to let's say, to parallelize your operations. And there are other constraints that is about the reduce of frequency and the use of shared control electronics that also put some limitations in what operations can be performed in parallel. So let's talk a bit more about the measurements. So as I say, qubit, for example, 13 and 16 are measured using the same feed line. So that means that if I want to measure both qubits, I can measure both of them simultaneously at time 0. For example, at time 0, I start a measurement of 13 and 16, and they can be measured at the same time. However, if I just want to measure one of them, if I start measuring qubit 13, and while running that measurement, I cannot measure qubit 16 at the same time, right? I have to wait till that measurement is finished to start the measurement on qubit 16. Yeah? Is that clear? Okay. Then the next constraint, as I say, it's about the frequency and how those qubits are operated. For example, in this picture, we use in the table at the top, we use 3 frequencies: the red one, the pink one, and then I use the same frequency for the green and the blue qubits. However, in this case, I'm using 4 different QWGs for controlling them. That means that, for instance, I can do an operation in parallel between qubit 4 and qubit 0. In other words, I can do an X in qubit 4 and at the same time a Z or a Y in qubit 0, because I'm using different AWGs for controlling qubits in spite of using the same frequency. But as you may know, QWGs, so AWGs, that stands for arbitrary waveform generators, they are very expensive, and having all of them apart, on top of that is not a scalable approach. So we want to let's say, optimize the use of those devices. So in that sense, we can think of using, instead of using 4 analog devices, arbitrary waveform generator devices, sorry, for controlling the qubits, I just use 3, 1 for each of the frequencies. In that case, for instance, it is possible to perform an X operation between qubit 1 and qubit 3 at the same time, but it's not possible, for instance, to perform an X operation in qubit 1 and a Y operation in qubit 3 at the same time. Yeah? So as you can see for this example, again, this limitation in frequencies and in sharing control electronics puts a limitation in what operations can be run in parallel, performed in parallel, right? And then we have to serialize those operations in your code. Now, there is an extra constraint, and it comes from how 2-qubit gates are performed in this kind of device. Do you know how 2-qubit gates are performed here? How to perform a CZ gate, a control phase gate?
I think you tune one of the qubits close to the resonance of a neighboring qubit.
Exactly. So if you want 2 qubits to interact, first, of course, they have to share a resonator, right, a bus between them, that's given. But on top of that, as I said, they are operated at different frequencies. So if you want those 2 qubits to interact, you have to bring one of the frequency of the qubit next or close to the frequency of the other one for interacting. And let's see an example. As I say, a C phase or a control set is performed by bringing the qubit, the frequency of one qubit next to the other one. And usually what you do is like you define the frequencies in a way that one frequency is higher than the others, right? In this case, F1 is higher than F2 and F2 is higher than F3. And by lowering the frequency of one of the qubits, they can interact. That if you look at the diagram here in the bottom, I have, for example, qubits D1, D2, they use frequency 1. Qubits X1, S2, Z1, Z2, they use frequency 2. And D3, D4 use frequency 3. If I want to perform, for instance, in this example, a C phase between D2 and X1, I have to lower, you see, you have to lower the frequency of the red qubit of DQ next to X1. But hey, what happens if there is a qubit also in the same frequency and they share a connection? What will happen there? And for that, we need to define other frequencies like F2 park and F3 park. What do you think those frequencies are just for?
I think it's just a frequency you can move to avoid being affected by other gates. Exactly,
because here's, for instance, I'm just lower the frequency of D2 for interacting with X1, right? By X1 is also connected, let's say, or D2, let's say D2. D2 is also connected to Z2, right? So in order to avoid Z2 to interact with D2, when performing this 2-qubit gate, you have to put it in what is called this par frequency or decouple it from the other qubits, okay? And of course, let's say the qubits that are in this parking frequency cannot do any operation while they are there. And again, that also limits the possible parallelism between the operations. Is this clear? Okay, if it is clear, of course, depending on the quantum device that you are considering, the constraints might be different. That, for example, this is the layout of a quantum device that was proposed by Menos group, in which it's a crossbar, a kind of 2D array with a spin qubits here. In this kind of device, for instance, when you want to apply a single qubit gate, you can only do it in all qubits in the blue columns, on all qubits in the red columns. And of course, you have to come up with a strategy for doing a single qubit gate in a single qubit, and that comes also with limitations in terms of parallelism of operations. Okay. So let's have a deeper look at what this mapping is about. Let's start with the placement of qubit and the scheduling of operations, how to do that. So again, imagine that I have the circuit here on the top, in which I have 7 qubits, and I want to run this circuit on the specific chip. On the bottom, it's just a 2D array of operations. So how to do that? So again, one of the first steps that I have to do is to place the virtual qubits into the physical ones, and ideally in an optimal way. And the other step that I can do is to schedule the operations. So for doing these two steps, the compiler internally, what it uses is what is called, in the case of the placement, a quantum interaction graph, and in terms of the scheduling, a quantum instruction dependency graph. So let's start with the placement. Now, again, I have the quantum circuit, and in order to place the qubits optimally, what I have to build is what is called a quantum interaction graph that is here on the top right. So just looking at this picture, can you tell me how to build, or what are the circles and the edges in this interaction graph? Just guess a bit.
I guess if any qubits I and j have to interact anywhere in the circuit, then you draw an edge between them in the graph.
Okay, so any circle on the interaction graph, it represents each of the qubits in the circuit, right? And the edges, can you tell me, Gay, the edges, please?
Is it the number of times they have to interact?
Exactly. So the edges, so they only have an edge if they interact, right? If they don't interact, for example, Q6 and Q7 don't have an edge because they don't interact. In other words, there is not a 2-qubit gate. By the way, here, when there is a control XX, it's like a control, I mean, it's just a CNOT. So the control X in 4X5, X6 is a CNOT between qubit 4 and qubit 5, and a CNOT between qubit 4 and qubit 6. So indeed, so there is an edge between the qubits here, only they need to interact, and the numbers in the edges are the number of times of the interaction that they have. So how many CNOTs they perform, or they do between them. So as I say, so the objective, or the main objective of the initial placement, is to minimize the communication overhead. Or in other words, you want to place the qubits in a way that they can all interact and they don't need to be moved. For that, you can, based on the interaction graph, you can build an interaction matrix. That's fine. And what you want to minimize is the communication overhead. And the communication overhead can be calculated as the sum of each of the weights, of the edges of the interaction graph multiplied by its Manhattan distance. So imagine that I have, again, this interaction graph and this chip layout or coupling graph, and then I come up with this initial placement, in which, again, Q7, the virtual qubit Q7 is placed in the left top qubit, and so on. If I do it in that way, it results with a communication overhead of 15. That in this case is the optimal one, I think. Okay. So the next step, once you have placed your qubits in the system, or in the quantum device, is to start the scheduling operations. And for that, what we need to build first is what is called a quantum instruction dependency graph. So a quantum instruction dependency graph looks like that, in which, again, you have nodes and edges. Can you tell me what are those nodes and what those edges represent?
each node is a gate that you have to apply, and each edge shows which gates are dependent on the operation of prior gates?
Exactly. So each of the nodes represent just an operation in your circuit. So I put G1, G2, so it's here the description on the left. And then the edges are the dependencies between the operations. In other words, for example, I cannot perform in G1, I cannot do G1 is Hadamard Q1, I cannot do a Hadamard in Q1 before initializing the qubit. So the Q1, Q2, Q3, Q4 means the initialization of the qubits to a specific state, in this case, state 0. Okay? So if this is clear, what I would like you to do, or we'll do it together, is to indeed build the quantum instruction dependency graph based on the instructions that we can see here on the left. So let's see if we can do that. So as I say, so the first thing is to initialize of the qubits to state 0, right? So then I will represent it with a paddle like that. You can see what I'm writing now, right?
Yes.
Yes, we can see it.
Okay, good. Just to make sure. So I just start by initializing every qubit. Then I go here on the left and I see the instructions and say the first instruction is G1, that is Hadamard on Q1. So I put here G1. So, and G1, I cannot do a Hadamard in Q1 before initializing the qubit 1, right? So that's why I can write an arrow from Q1 to G1. The same for G2. So G2 is Hadamard Q2. I cannot do a Hadamard on Q2 before initializing the qubit, right? So that's why there is an arrow from Q2 to G2. And in a similar way, G3, an arrow from Q3 to G3. The next one is G4. That it's a C node between Q4 and Q5, right? So Q4 and Q5, there are no operations before, just initialization. So that means that this operation depends on this one. Then G5. What about G5? G5 depends on Q4 and Q6. So I cannot perform that one before initializing Q4 and Q6. Any questions so far? No? Is it clear for everybody why, for example, I put on the same level G4 and G5 and I didn't put a dependency between them? Because there is Q4 in common, right? They have the same qubit. They use the same qubit.
But in G4, Q4 is just a control qubit, so it isn't really affected by it.
Exactly, but then, so I just, by building the interaction graph, so here I put G4, G5, and I didn't put any dependency between them, but actually we will see when we start scheduling the operations, we cannot run them in parallel, right? So it's up to the scheduler and the optimization technique that you are using to decide which one to schedule first, right? Which one to perform first. Yes?
So when we make this graph, we ignore the problem that, for instance, you can't bring both of the frequencies of Q5 and Q6 close to Q4 to implement the C0.
You don't. So here it's not only about that. It's not about the frequencies. So that here I'm just talking about the dependencies without taking into account other constraints that the chip might have, right? Because that might put more restrictions there. Here I'm just talking about dependencies between the instructions. So in the dependency graph, you can already maybe say that you have to perform first Q4, Q5, and then Q4, Q6. You can say that, right? But those gates, these two gates, they commute. So it's up to, so you can you can just not put any dependency between them, and then it's up to the scheduler to decide which one to perform first, right? but for sure they cannot be performed in parallel. Is that clear?
Yeah.
Yeah? Okay. Then we go to G6. And G6 is a C node between 3 and 4. So between 3 and 4, so that depends on G3, right? Because there is a hallmark before, and between 3 and 4. What arrows are missing here? What arrow you will put there to G6? I just put the one from G3. What other arrow or arrow you will put there? From which instructions, I mean, from which operations this C node Q3, Q4 depend?
A line from the original Q4, right?
A line from the original Q4? I'm not sure.
Is it from G4 and G5?
Exactly, G4 and G5. Because in this case, I cannot perform G6 till G4 and G5 are performed, right? Because imagine if I do C6 before the other two, that will change the state of Q4, and then the result of the C node of Q4, that is the control with the other two qubits, might change. Yeah? Is it clear? And then we go to G7. And G7 is a C node between Q3, so it depends on this one, and Q5. And Q5, G4 has been used in G4, so I put another dependency there. Then I go to G8, and G8 is a C node between Q3 and Q7. That Q7 has not been used before, so that goes directly from there. Yeah, let's go. Let's do one more, G8. Now I go to G9, sorry. Oops. I go to G9. And this is a C node between Q2 that has not been used in here. So Q2 and Q4. And Q4 has been used here before G6. Then I go to G10. And G10 depends on Q2. And Q6. Q6, the last time it has been used is G5. And then I go to G11. G11, that depends again. I will do like that, sorry for that. On this one. And 7, that is has been used in 8. And so on. So there are two. Is it clear for everybody how to build a quantum instruction dependency graph?
For G9,
Mm-hmm.
do you have also put an edge between G7 and G9?
G7.
Q4?
Sorry, oops. G7 doesn't have Q4, has Q5. So there is no dependency between those two.
Okay.
Yeah, why do you want to put an H there? Because G9 depends on 2 and 4, and G7 is using 3 and 5.
G7 uses G3 and G4, right?
G7, no, 3 and 5.
Oh, okay.
That's G6.
Okay.
I don't know if I made any mistake. I hope not. G6, G9, 6, 7, and 10, 5. Yeah. I think I didn't make any mistake, but yeah, you can double check afterwards. So if you continue doing like that, at the end, you will build, again, the quantum instruction dependency graph that I just mentioned. It's important that you understand how to build it. If it's not clear, so just try it yourself. If it's not clear, please let me know, because in the next homework, yeah, that will be post it on Friday, you will have to build a quantum instruction dependency graph. Okay, so we stop here and we continue in 15 minutes. Okay, let's continue with the second part of the lecture. So let me start. Cool. Is there any question about the quantum instruction dependency graph, how to build it? I will take that as a no. Can you hear me? Are you there?
Yes.
Yes.
Okay, good, because I thought maybe I forgot to switch on my microphone. Okay, so as we have seen, the first thing for scheduling operations is to build a quantum instruction dependency graph in which each of the nodes of the boxes represent an instruction and each of the edges the dependency between them. Here again, I just show the dependencies among the instructions, not considering any other constraints of the chip as the frequencies of the SIM, how to perform the C phase and so on. Now we have to do, once we have the quantum instruction dependency graph, the next step is indeed to schedule operations, because these just show the dependencies, but the operations has to be scheduled. There are different ways of scheduling the operations, but one of the most used approaches is using an as soon as possible scheduling or as late as possible scheduling. What do you think it means as soon as possible?
If all mandatory operations before an operation have been completed, then schedule the next operation as soon as possible.
Yeah, indeed, as the name suggests, what it means is that you have to schedule them once the previous operations, as you mentioned, has been, let's say, executed. You have to schedule the next operations in as soon as possible manner. And on the contrary, as late as possible is the other way around. So I try to perform all the operations as late as possible as I go through the quantum instruction dependency graph. So knowing that, so again, let's take the code that we saw before with the quantum instruction dependency graph, and let's try to schedule the operations in an as soon as possible manner. So for that, I'm going to define different cycles, right? I'm going to say, for instance, in cycle 0, what operations can I perform before? So if I look at the quantum instruction dependency graph and I look at the code on the top left, what instructions I can perform in Q0, for instance? In C0, so in cycle 0.
In cycle 0, G1, G2, G3, G4, and G5.
Wait, the first thing is to initialize the qubits, right? I'm also considering that. So in cycle 0, I will just put, yeah, initialize. I mean, when you write this in just say the QX simulator, you have to put preset, right? But I will write it as it is in the slide: Q1, Q2, Q3, Q4, 5, 6, and 7, right? Good. Now I go to the next cycle. As I'm initializing of the qubits, for sure I cannot do any other operation in parallel while doing that. Now, in C1, what operations can be performed in C1? What do you think?
G1, 2, 3, 4, and 5.
G1, 2, 3, 4, and 5. 4 and 5 can be performed together.
I think you have to wait to do 4 before 5 because the gates, 4 needs to be coupled to 5 before it can be coupled to 6.
Exactly. So here there are, as I mentioned at the beginning, I consider that those, so the gates that CNOT gates that share the same target and the same control, sorry, and different target, and in this case, this G4 and G5, or in other words, CNOT Q4, Q5, CNOT Q4, Q6. It's up to you. They commute, then it's up to the scheduler, in this case, to us, to which one to schedule before, right? So in other words, if I do CNOT Q4, Q5, I cannot do at the same time CNOT Q4, Q6. Yeah. because they share the control qubit. Is that clear?
Yes.
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 Therefore, here I can do Hadamard Q1, Hadamard Q2, or just to put it in a very simple way. I mean, if I'm using Q4 for doing something, I cannot use Q4 for doing something else, right? If it's involved in one operation, I cannot involve the qubit in a different operation. Yeah, just Q3, and then, for example, I just put G4, that is the C naught, Q4, Q5, right? Now I can also go through the dependency graph and to the next cycles to see if I can put any operation there. So, for example, can I put there in the same cycle Q3, Q4? Can I put in the same cycle, for example, this one? Can I perform in parallel Hadamard Q1, Q2, Q3, C naught, Q4, Q5, and C naught, Q3, Q4? That is G6.
No, because it needs G4 and G5 to be done, and we only have
Exactly.
one of the two.
Exactly. Correctly. Yeah. So then I go to the next cycles, 0, C1, C2. I'm just going to cross the ones that we already scheduled. Okay. And then I'm going to put here C naught, Q4, Q6. Yeah. Can I schedule any other operation in that cycle?
I think we can also schedule G8.
G8 is G8 37. But let's go in order. Can I schedule any other before? So I'm here, right? I just schedule this one. Let me see. 3, 4 cannot be scheduled, right? Because I'm using 4, 6, so it cannot be scheduled. 3, 5. Can we put 3, 5 there? Just to go in order and use the same as you will show on the slides. Can I put here in the same cycle C naught in cycle 2, C naught 3, 3, 5, Q3, Q5?
Yes.
Yes. C naught. Q3, Q5, then I cannot put Q3, Q7, of course, Q2, Q4, and so on. So let's go to the next cycle. Then I put 3, 4. What else can I put there if I go in order? Can I put 3, 7 in the same cycle? C naught, Q3, Q7?
No, we're already using Q3, so.
You're using Q3, Q2, Q4. Let me see.
No.
No, because I'm using Q4 too. Can I put Q6? See, no,
Yes.
Q2, Q6. Yeah. Can I put Q7?
No, because we're also already using Q2.
Yeah, and Q1, Q5?
Yes, you can.
Yeah, good. So I can put. Then I put here C naught 3C. I'm here now, right? So I'm going to put C naught, Q3, Q7. Yeah. I can put C naught, Q2, Q4. Yes, because I'm not using any of those qubits, right? So I can write on that one. Then Q1, Q2, Q7, I cannot, right? Because I'm using Q2 here. And Q1, Q6, I can write. So that brings me to the next cycle. That is C naught, Q2, Q7, and to the next cycle that is C naught, Q1, Q7. Yeah. Is this clear for everybody?
For me, it's clear.
Yes. So I just scheduled based on the dependency graph. I mean, I'm looking at the instructions here and looking at the arrows. I can build them as soon as possible scheduling. Now, if I do that, we just do what we obtain is this here. That is exactly what I show in the previous slide, and I can just kind of reorganize. Just is for you to visualize it better. I can reorganize, let's say, my quantum instruction dependency graph in different cycles, complying to the edges or to the dependencies between the instructions. Yeah. Now, but as I just mentioned, there is another way of scheduling the operation that is as late as possible. So in the first case, in the as soon as possible, we push all operations to the top. But now we are going to push all operations to the bottom, right? And to schedule them as late as possible. So how to do that? So the easiest way to implement a lab scheduling as late as possible is to start with the previous one, with the as soon as possible scheduling, with the ASAP scheduling. And how to do that? Let's see. So the first thing, I start in reverse order. So I start with cycle 6 and I put C naught, Q1, Q7. And what I will try to do is to push all the instructions as much as possible to the bottom, yeah. So in other words, I'm just going in the reverse order. Now I go to C5. Can I move C naught, Q2, Q7? This one I can already remove, right? Because it's already there. Can I move this one to cycle 6?
No, because it's also using Q7.
Because it's also using Q7, right? So it has to stay there. Okay, this is done. Now I go to the previous cycle. Can I move this one, Q3, Q7, to any of the other two cycles? Here or here?
Again, no, because it's using Q7.
Exactly. Thank you. What about Q2, Q4? Where can I put Q2, Q4?
Can we put in cycle 6?
We can move that to cycle 6, right? I cannot put it here because there's 2, but there's no dependency between those two. I can move. Yeah? What about Q1, Q6? Where can I put this one, Q1, Q6?
In cycle 5, I think.
In cycle 5, yes. I cannot move it to cycle 6 because Q1 is here, right? So I cannot put those two, so I leave it there. Yeah, good. I'm done with this cycle. Then I go to cycle 3. I start looking here. What about Q3, Q4? Now in here.
Again, cycle 5.
Yeah. What about Q2, Q6?
Cycle 4.
Q1, Q5?
Also to cycle 4.
Mm-hmm. Good. Now I'm here. cycle 2. 4, 6. C0, Q4, Q6.
Cycle 3.
Mm-hmm. C0, Q3, Q5.
Also cycle 3.
Q3,
Right,
Q5. Yeah.
Yes, or cycle 6, but
Cycle 6, yeah, but in this case it can be done to cycle 6, but because I put a dependency between this instruction with this instruction, because this instruction Q3, Q5, let me see which one it is. So Q3, Q5 is where is it? I didn't put the name there. Is G7. G7 is Q3, Q5, right? And G12 depends on G7, and G12 is again Q1, Q5, and Q1, Q5 it's here.
yes, so it's
And depends on that one. So in principle, I cannot put it there. But because here, I didn't consider that also gates, C0 gates with the same target also commute, right? And I put already a dependency between them. If I will consider that, I can move it down to C6, okay? But I didn't consider that because if not, it makes more complex the problem. And then you can come up with completely different solutions, okay?
yes.
So if we assume indeed that's dependency here, then C0, Q3, Q5 should stay here, yeah? But if there was not that dependency, that there was not that edge between 7 and 12, if I didn't have that edge here, because I consider commutativity rules, then I could move it till cycle 6, yeah? Then this is done. What about Hadamard Q1? Where can I put Hadamard Q1? I'm here now. In which cycle?
C3.
C3, exactly. Because the qubit Q1 is not used till here, right? In this operation, so I can put that, push it there. Hadamard Q2.
Also cycle 3.
Okay, exactly. Hadamard Q2. Hadamard Q3.
Cycle 2.
Mm-hmm. Yeah, because I start using 3 here, right? And C0 4, 5.
Cycle 2.
Yeah, exactly. And what about the initializations then?
Cycle 1, right? Because
We can also push the initialization, the preparation of the qubits, right? We don't need to let's say to initialize the qubit all of them at the same time.
No, true.
So I will say that in cycle 1, I need to initialize for sure Q3, right? Q4 and Q3, Q4 and Q5, right?
Yeah.
3, 4, and 5, because I'm using them in cycle 2. Then the others, let me see which ones I need to initialize here. I need to initialize 1, right? Because I'm using it in the next cycle.
Mm-hmm.
I need to initialize Q, Q2, Q6, and Q7. I'm not using it till C4, right? So I can initialize Q7 here. Sorry for that. And then I'm done. And you see now with using this other scheduling, as late as possible scheduling. So before we had like 7 cycles from 0 to 6. Now I save 1 cycle with 1 to 6. So I'm using 5 cycles. Yeah. And what do you think about that? I mean, that's not the case all the time. So sometimes they use the same cycles, or it can be more advantageous as soon as possible. I mean, that's not the case all the times. But if you had to choose, do you see an advantage of using as late as possible scheduling compared to as soon as possible?
Less,
If you
less
had to choose,
cycles is the, or do you mean in general?
yeah, no, in this case, we obtain less cycles, but that's not always the case. Sometimes you can even get the same number of cycles, yeah? Or it might be some cases in which, I'm not so sure about that, but it might be some cases in which you can even have higher number of cycles, but that I'm not sure. But it's not about the cycles. Think about the initialization of the qubits.
Resource utilization, maybe.
Resource utilization. That's one thing, yeah, because but in as late as possible, you measure, you push the measurements at the end, right? So in as soon as possible, if, for example, you think about measurements and you measure as soon as possible, then you can reduce that qubit if you can reduce for other things. But think about initialization of the qubits. In the previous case, in as soon as possible, I initialize all of them at the same time, right? I prepare all of them at the same time. And in as late as possible, I just prepare them before they are actually used. And of course, you can reduce it before for other things, but also what happens when you initialize the qubits, all the qubits at the beginning?
If you initialize all of them together, but then you don't need some of them right away, then they're just sort of idling and they might pick up errors.
Exactly, because of the coherence and because of the errors, right? So they may decohere, and whenever you want to use them, you have to prepare them again, right? So that's why maybe this scheduling is more advantageous in that sense. So just to see the differences. So if this is clear, so at the end, so here on the left, you can see the as soon as possible scheduling that we have done, and also the late as possible scheduling. If we look again at this quantum instruction dependency graph, as I said before, it's up to you if you want to do for G4 or G5, right? Because that's a CNOT between 4 and 5 or a CNOT between 4 and 6. In this case, we chose to schedule first G4, but if you schedule first G5, you get this different schedule in which you can see here that you need one less cycle than in the one on the left. Yeah, and for as late as possible, scheduling first G5, that is just going in reverse order on the top as soon as possible scheduling, you still get the same number of cycles. So again, depending on what commutativity properties you are considering, and also depending on how the scheduler chooses or the gate, you can end up with a better scheduling in terms of cycles. Any questions so far about the scheduling and the instruction dependency graph? No? Okay. So let's make things a bit more complicated or a bit simple. So in the previous exercise with the scheduling, we have considered just physical qubits. But now imagine that we have the same circuit, but instead of having physical qubits, each of these qubits, Q1, Q7 in the circuit, is a logical qubit, and they have been encoded using surface code. As I mentioned at the beginning of the lecture, there are two ways of encoding logical qubits in surface code. The one is using a planar-based approach, right, in which a patch of your lattice is a logical qubit, or just making holes. So when you schedule, let's say, logical operations is different from scheduling physical operations, and I will explain you why. Because in defect surface code, there is something that is called, it is possible to perform a single control multiple target. In other words, so just let me go to the previous slide. So as I explained in the previous lecture, in order to perform a CNOT between two defect logical qubits, you take one of the holes and then you go around one of the holes of the other logical qubit. So in principle, by using this technique of braiding, you can perform a logical qubit, a logical CNOT between a single control and multiple target, because this hole can go around of different let's say target qubits in your lattice. If you can do that, of course, this is theoretically, because of course physically you have to make sure that you can find a path for doing that, for doing around different holes, and then there is no let's say collision with other movements or change or to change the distance of the code. Okay, so if that's possible, that means that, for instance, I can do a C0 Q4 Q5 and a C0 Q4 Q6 at the same time, because that will mean that it's just the whole of the Q4 going around of the holes of the Q5 and Q7, right? In other words, I can perform single control multi-target C0 operations. Okay. Now, assuming that we have encoded our logical qubits using this defect-based approach, and assuming again that by doing that I can do single control multi-target CNOTs, can you please derive the as soon as possible scheduling based again on in the dependency graph on the right? I will give you 3 minutes. Is it clear what you have to do? We are going to schedule again the operations using an as soon as possible approach, and assuming that now qubits are logical qubits that has been encoded using defect-based logical qubits, and with these qubits you can do single control multi-target CNOT operations. Anyone who wants to tell me what operations I can perform in C1 in this case?
Is it G1 through 5?
G1 till G5, all these ones, right? So I can do Hadamard Q1, Hadamard Q2, Hadamard Q3, and because I can do single control multiple target, I can do Q4, Q6. Yeah. In cycle 2,
is it 6, 7, 8, 10?
6, 7, 8, and 10. Yeah. I'm going to put just like that because it's easier. 6, 7, 8, these 3, right? And this one, 2, because there is G8 and G10. Cycle 3.
9, 11, 12, and 13.
9, 11, let me double check. So 9, 11 to 4. 6, 9 to 4, 11 to 7, yeah. Which one you say? Sorry, again, 9, 11?
12 and 13.
Let me see. Mm-hmm. Yeah. 12 and 13. Yeah. And here, just missing G14, I think, right? Is this clear for everybody? Yes, I take that as a yes. So indeed, if I do it like that, so then I come up with this open scheduling in which I need just 5 cycles to perform all the gates in the circuit. And again, so what now if I want to do an as late as possible scheduling? So by doing from bottom to top of the graph or of the instructions, I can push all operations to the bottom cycles, and I can again obtain this as late as possible scheduling, in which in this case I require the same number of cycles. Okay, so but can we do better? So here, when we were scheduling operations, we were assuming that all operations take the same time, right? Because I was assuming, okay, for example, in cycle 1, I can do a hallmark in Q1 together with a C note in Q4, Q5. Is that what happens in reality? All operations do all operations take the same time?
I mean, like at least for superconducting cubes, typically the 2-qubit gates are slower.
So usually, performing a 2-qubit gate takes more time than performing single-qubit gate. And for example, performing a measurement is one of the most expensive operations in terms of time. So if we consider that, we can still do better. Why? Because again, all gates here we have considered that they have the same gate duration, but that's not the case. If we do that, if we just take the scheduling that for the phase-based logical qubit, we schedule it in as soon as possible. We can see that if we consider that the cycle, let's say the cycle of the duration, or the duration of the cycle is in this case the time of a CNOT gate. So in this slot, for instance, there is a CNOT gate, but still I could perform, if there were some operations, I could still perform some other operations here, right? That becomes more, now you can see it better in this other scheduling, in which again is the defect-based logical qubit that I use as late as possible scheduling. And in the same cycle, I can do a CNOT, but I can also do the preparation of the qubit Q2 and the Hadamard Q2, still one after the other, but within the same time I'm performing the CNOT. And I can reduce the latency up to 91 quantum operation cycles. And again, if I do the same, but for example, now for a planar-based logical qubit, I can see the same kind of operations performing in parallel in a single cycle, in which while performing, for example, CNOT Q4, Q6, I can do the preparation and the Hadamard on Q2 and Q1 at the same time. Yeah, and I can save some cycles there. Now, together with one of my PhD students, Lynn Lau, so what she developed a scheduler for logical qubits as well for physical qubits. Here I'm just using the logical qubit, in which we compare how many cycles in terms of surface code cycles, how many cycles you can save when using just a cellular scheduler. That just means one operation after the other. So with an if scheduling, just not taking any into account any commutation rule, or with a proposed a lab or sub-scheduling in which we take into account the commutativity of the gates. And as you can see, we can save some latency of some cycles by doing these optimizations. The other thing is also when you go to logical qubits, what about the placement of the circuits? So when you want to, let's say, perform computation using logical qubits in your quantum plane or in your chip, you have to define a kind of virtual infrastructure. I mean, like you have to define places where you can place your logical qubits, because now a logical qubit is not a single qubit anymore, it's a set of physical qubits. So also with my student Lin, we propose two different, let's say, architectures of virtual organizations for the quantum chip. The one is the checkboard on the left and the tile base on the right, and they differ on the following parameters. So they differ on the number of logical qubits that they can allocate. That, for example, on the figure of the left, you can allocate a logical qubit for computation in each of the pink areas, and on the right, you can allocate them either on the pink or in the purple areas. They differ in the way that movement operations are implemented, because we will say we'll have to move qubits around, especially when you want to do a CNOT between two corner qubits. Remember that you have to use this L shape, and then you use lattice archery. And for that, qubits need to be nearest neighbor. So you can move those logical qubits in different ways. They differ in the number of qubits that they can interact, the number of neighbors, and also the execution time of the CNOT between different data qubits. So by doing that, we just perform some experiments, and of course, here on the one on the left, the checkboard, it allows you to, let's say, place more logical qubits in your device, but also put more constraints in the movement of those qubits. On the other hand, the one on the right, you can place less logical qubits in your device, but you have more freedom for performing operations and for moving the qubits around. And that's why the TR, so the one that will less, let's say, logical qubits, can reduce the operation overhead and the latency overhead, because it has more space, let's say, for performing the operations. Now, so far, as I mentioned at the beginning, there are three main steps in the mapping process. That it's about placement of qubits and scheduling of operations that we just discussed. But there is also another step that is called the routing of qubits. So the routing of qubits is about putting the qubits next to each other when they need to interact. So imagine that you have those two physical qubits and they need to perform a CNOT, and of course they cannot interact. So I have to move one qubit next to each other in order to interact or to perform a CNOT. And for that, how can I move qubits around, or how can I move quantum information around? I can use swap operations that they just exchange the state of the two qubits that are usually using superconducting qubits. I can use teleportation, but that's more complex because you have to have to generate EPR pairs with high fidelity, and then you have to distribute them between the source and the origin and so on. So that requires a lot of resources too. Or you can, in other technologies like in silicon spin qubits or ion trace, you can just shuttle the qubit itself. Now, again, just an example of a routing. Imagine that I have this qubit layout, and I place the logical qubits in the physical qubits like that. And then I need to perform a CNOT between Q1 and Q8. As you can see in the figure, Q1 and Q8 are not next to each other, and therefore I need to route them, right? How to do that? So I just need to perform two SOT, for example, between Q1 and Q2, and Q2 and Q5. But is that the only possibility for those qubits to interact, or I can't do any other swaps or movements? If I need Q1 and Q8 to interact, I can only do these swaps, those two swaps here, or I can do something different.
You could swap to 4 and then 5, or 4 to 7.
Yeah, I can also do this here, right? And it's still two swaps. So indeed, the routing step, it's about finding the path that brings qubits to adjacent positions when they need to interact, and then insert the corresponding move operation, right? And for that, you can have different shortest paths or different options. So what happens when you do the routing is the routing usually increases the number of gates in the circuit and therefore the circuit depth, and that decreases the fidelity or the probability of success of your algorithm because of the reasons that we just mentioned before. So that's why during what the metrics that usually are optimized during the routing process are the number of swaps, and how you optimize that is just choosing one of the shortest paths. So you calculate different paths between two qubits and you just take one of those shortest paths. You can optimize them based on circuit depth, and that means that when you optimize on circuit depth, you can take one of the shortest paths that it interleaves very well, let's say, with the previous operations, or it might be that it's more advantageous to take a longer path that interleaves better with operations, okay? But at the end, what you care about, so the number of swaps and circuit depth, as I say, they are correlated with the reliability or the fidelity of your algorithm, and that's what you care about at the end, right? Here in this graph, you can just see the fidelity of an algorithm before mapping and how that fidelity is decreased after mapping into a specific chip. That's why there are some people that are starting doing the mapping based on the fidelity of the links between the chip. Because something that I didn't mention, that's something, for example, that you can observe in IBM chips, is like performing a CNOT, for example, in this case between Q0 and Q1, has a higher fidelity than performing a CNOT between Q1 and Q2. So in this work, what they did is to observe, let's say, or to observe the fidelity of these links among different in 26 days, because these fidelities also change among the days, calculate the average and come up with this kind of a layout. Again, in which the numbers here, those represent the fidelities between each pair of qubits or the fidelities between a CNOT between those pair of qubits. So whenever they want to route a qubit or to find a path, what they do is to choose the path that has a highest fidelity. That, for instance, if I want to perform a 2-qubit gate between Q1 and Q6, I have two options, right? Or either I take this, I put this qubit here, and I perform the CNOT, or I move this qubit here, and I perform the CNOT, right? So as you can see here, these links, 09 and 08, have higher fidelity than those two links. Therefore, I will choose this path in my router. Okay, by doing that, they use this mapper for running different algorithms on different qubit topologies or qubit devices from IBM, Rigetti, and UMD, and they calculate the success rate for some of them. If you look at this graph, there is one chip that is the UMD that has the highest success rate. Why is that? And on top, you can see the different configurations of the different chips.
It's because the UMD trapped ion is a complete graph, so all the nodes are connected to each other.
Exactly. So in this case, in this 5 ion trap device, it's an all-to-all connectivity, and therefore there is no need for routing. So you are not adding any extra swap or any extra shuttling operation in your algorithm, right? Yeah. So here in Dell, we have also developed a mapper for the Surface called Surface 17 chip, taking into consideration all the constraints that I explained before, but it can be also used for mapping algorithms on the IBM Q Tokyo chip. Just to show just the big picture, I mean, how usually mappers are implemented. So mappers, as I said, they are implemented within the compiler, so it's a compiler pass. And they have different steps, like the ones that I mentioned, that are initial placement, the router, and the scheduling of operations. And of course, you can also do some optimizations that cancel gates. And in order to do that, what they use is what we call a configuration file or JSON file, in which all the, let's say, constraints or the characteristics of the device are described and for doing this mapping process. That's, for example, in this configuration file, we have what are the elementary gates for doing gate decomposition, what is the duration of each of these gates, what is the chip topology, so how many qubits and how they are connected, on, for example, the classical control constraints that I just explained about the number of TWGs, and how they are connected to the different frequencies of the qubits. Yeah. So with this, I would like to finish the lecture. So what we have learned today, or I hope you have learned today, is that quantum algorithms need to be compiled or mapped to a version that complies to the constraints of a chip. These chip constraints may vary between different, let's say, processors and technologies, but they are usually, they can be summarized as limited connectivity between the qubits, limited gate set, and the use of shared control electronics. And the mapping consists of three steps, or three main steps. That is the initial placement of qubits or mapping of qubits, the routing of qubits when they are not nearest neighbor, and the scheduling of operations. And in the routing step, that is one of the key steps because it's the one that adds operations. The metrics that are usually used to optimize are the number of operations, the circuit depth latency, or even the reliability, let's say, of the algorithm, taking into account the reliability of the different peaks. And as I just mentioned, the mapping process increases the number of operations and the circuit depth, and that decreases the success rate of the algorithm. Okay, so any questions? No questions? No. So with that, we finish today's lecture, and we finish with the part on quantum computer architecture of this course. So next Friday, it will be my colleague Fabio Sebastiano who will be teaching, and you will start with the second, let's say, part of this course on the low-level electronics for controlling and operating of the qubits. And then I will see you again at the end of the course. Yeah. If you have any question about what I explained today or any of the lectures, please let me know. I will be happy to answer any questions you might have. I hope you have learned a bit in this part about quantum computer architecture, and I hope that you enjoy the rest of the course. Okay?
Okay, thank you.
So thank you very much, and then I will see you in a couple of weeks again. Bye.
Bye.
Bye.